Sometimes when we talk about probability, we have additional information. So to illustrate that, let's say I flip two coins. So what is my sample space? Well, omega equals, I could get heads, 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 tails, tails, heads, and tails, tails. Now we can all agree that these are equally likely events if I have no additional information. But what happens if somebody tells you something about the flip? So I flip the coins, I look at them, and then I tell you something else. What if I tell you that I didn't get two tails? So that's equivalent to saying at least one of the coins is heads. So now if this is our sample space, and let's say this is tails, tails, heads, 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 tails, tails, heads. And I'm saying, well, I kind of threw my dart at this board, and I'm telling you I didn't land over here. So how does that affect what I think the probabilities are of these guys over here? Well, I didn't give you any information about how their relative probabilities change, so we think they should all be the same, and given what I just drew, the intuitive answer is probably 1/3. So let's do this a little bit more formally. Let's let A be the probability that I got heads, heads. So let A be the event heads, heads. And let B be the event not tails, tails. I didn't get two tails. So now I say, what is the conditional probability of A given B? Well, here's where we introduce just the definition of conditional probability. This is a definition. The probability of A given B for any two events is the probability of A intersection B divided by the probability of B. So what this is saying is that if I know B, probability of B, if I know B, then I'm basically making a new omega, a new sample space, by saying I have A, so let's say A is over here, this part of the space, and then maybe B intersects A to some degree, and then this is B. So I'm telling you I landed in here. What's the probability that I actually landed in A, given that I landed in this region? And we know that the probability of the whole space should be 1. So if I make this area my whole space, this should be 1. So that's why I divide by the probability of B. And A intersection B just says take the region that intersects B, because this area out here doesn't count anymore. So this is the unconditional area of where it could be both of them. And then this is just the unconditional area of B. So in our example up here, well, the area of A, so P of A intersect B, you have A intersect B is equal to, well, it's only this event, so it's 1/4. And then what's the probability of B? The probability of B, well, not tails, tails means I could have been here, I could have been here, I could have been here. That's equal to 3/4. So plug these in over here, and we get 1/3. Jives with our intuitive answer. Note that I specified that I didn't get tails, tails, so that means one of the two is heads, at least one of the two is heads. If I had told you that the second coin was heads, I would be restricted to these two events, and I would get the answer 1/2. If I told you that the first coin was heads, I would get this and this. So it would still be 1/2. The lack of information about which coin came up heads made the probability different. Now, one other thing to note that will lead us into our next topic is that there was nothing special about the labels A and B here. I could write the probability of B given A for any events B and A. Well, that's also equal to the probability of the intersection of B and A, but the intersection of B and A is the intersection of A and B. They commute, divided by the probability of A. So this over here is equal to this over here. So the probability of A given B, if I multiply through, times the probability of B is equal to the probability of B given A times the probability of A. Now notice that I don't have this intersection in here anymore. Very frequently, we're not interested in this intersection because either we don't know it or it's too hard to compute, but we do know one of these conditional probabilities and we want to find the other. So what this is going to let us do is this is going to let us write something we don't know in terms of something we know. And whichever one of these is easier to compute will help us find the harder one.